Hi, this is Jerome from CWRU. Today I'm going to present our results in measuring the support for DNS over TCP in the internet. Here are the topics we're going to cover today. We're going to look at the DNS over TCP support on two sides of the DNS infrastructure, the recursive resolver side and authoritative DNS server side. We focus on the support on those two sides because they are where we can directly associate the TCP support behaviors to the actors that are responsible for them. At the end of the talk, I'll briefly discuss the race condition between the recursive resolvers and ADNS servers in DNS over TCP. So let's look at the TCP fallback support by recursive resolvers. Later, I'll just use resolver, which is equivalent to recursive resolver or recursor. So the general approach is that we want to measure as many resolvers as possible. We want to force the resolvers to talk to our ADNS through TCP. So what we did is our ADNS sent truncated UDP responses to the resolvers, and those responses have no resource records set up. Therefore, if the resolvers want to complete the resolutions successfully, they have to fall back to TCP protocol. We have 4 datasets. The first one, an open IPv4 resolver scan with unique queries to our own domains. The second one, we use bouncing messages in SMTP protocol. So our scanners send email to non-existing recipients at the domains from the Majestic top 1 million list from our own domain. Those mail servers, they won't be able to deliver this email, and we can expect bouncing messages for delivery failures. And those mail servers, we're going to query our MX records, and our ADNS, we're going to force TCP fallback in MX resolutions. The third dataset, we use the famous RIPE Atlas platform. So we let the RIPE Atlas probe to send unique queries to our own domains through their resolvers. And the last dataset, we have the ADNS logs from a major CDN. These logs are highly aggregated, so we only use these logs to assess the real-world activity of the resolvers from different categories. And here's the challenge. TCP fallback is a two-step process, so it is hard to associate the DNS over UDP queries and DNS over TCP queries. And because of the collaborative resolution, it is even harder. So our definition for TCP fallback capable is that either a resolver itself is capable of fallback to TCP, or this resolver has a peer that falls back to TCP for it. So the figure on the left shows a simple canonical scenario of a TCP fallback process, a UDP query and a TCP query for a unique query name. So in this case, we can say that this resolver is TCP fallback capable. And this is a more complicated non-canonical scenario. So we are still talking about unique query name, and now we have two UDP queries from resolver A and B, and a TCP query from resolver C. In this case, we do not have enough information to say that the TCP query from C is a consequence of A or B's UDP transaction. So both A and B are indeterminate in terms of the TCP fallback capability in these transactions. And in fact, these non-canonical scenarios, the non-canonical scenarios like this, are common and account for about 50% of the resolution patterns we've seen. And we have developed an algorithm that tries to find an unambiguous 1 UDP to 1 TCP query matching and label the fallback capabilities of the resolvers by the outcome of the matchings. Just like what we've seen in the previous slides, some DNS transactions, they just don't allow unambiguous inference of TCP fallback capability. So we have two estimations, the optimistic and pessimistic estimations. And the only difference between optimistic and pessimistic is how we process the indeterminate labels. In optimistic estimation, we consider indeterminate as TCP fallback capable, and in pessimistic, indeterminate is TCP fallback incapable. So throughout all three datasets, we've discovered 116,000 resolvers, and about 95 to 97% of them are TCP fallback capable. So we use a range here to represent the number of TCP fallback capable and incapable resolvers according to the optimistic and pessimistic estimations. The TCP fallback capable resolvers, they contribute to around 96 to 99% of the CDN traffic from all the resolvers we've studied. So the takeaway here is that there is a non-negligible number of TCP fallback incapable resolvers, and those incapable resolvers are just about equally active as the capable resolvers. Now let's move on to the TCP support by ADNS servers. So in those measurements, we're going to act as resolvers. So we have the control over the transport, and the general approach is just we try to send TCP queries to the ADNS servers serving certain domains from a testing machine on campus, so we only use one single vantage point. And we have three datasets here. The first dataset includes the domains from queries handled by the resolution service operated by the major CDN. The second dataset is the majestic top 1,000 root domain websites, and we call those popular websites. And the last dataset, we have a list of CDN accelerated domains, and we pick one domain per CDN. And we test all ADNS servers listed for each domain in those three datasets. Here are the results for the TCP support by ADNS servers. First of all, for the domains from queries handled by the resolution service operated by the major CDN, more than 5% of the domains, they just fail to resolve a TCP query through some ADNS servers. And even for the popular websites, still a little bit more than 3% of the domains, they just fail to resolve a TCP query through some of their ADNS servers. And for CDNs, 11 out of 47 CDNs, they have deployed ADNS servers that do not support DNS over TCP. And let's look at the race conditions that applies for the ADNS that do support DNS over TCP. So first of all, RFC recommends reusing established TCP connections. And in fact, the resolvers, they do reuse connections. In another email scan, we have successfully induced 13.5% of the enterprise resolvers to reuse TCP connections. And this is a race. A server tries to close the connection after sending out a response, and the client is trying to reuse this connection for further queries before knowing that the server is closing out this connection. So we can see that the client's follow-up query is going to be left unresponded. And in fact, about 33% of the popular websites and 4 CDN providers, they deploy ADNS servers that just close the connections immediately after responding to the first DNS query in these connections. Here's the conclusion for today's talk. So first of all, on the recursive resolver side, a small but non-negligible number of the resolvers, they do not support TCP fallback, and they are active. And for the ADNS servers, still a non-negligible number of top websites and CDN providers, they use ADNS servers that do not support DNS over TCP. And for the ADNS servers that do support DNS over TCP, many of them are vulnerable to the race condition.